Your write came back 200 okay. You read it again and it was gone. No server crashed, no disk failed, nobody deployed anything. For about 40 seconds, two racks could not reach each other. That is the whole incident, and your database behaved exactly as designed. Here is the shape of it. Picture a checkout service on a Friday. Two customers touch the same cart from opposite sides of the break. Both sides say yes, both sides are telling the truth about themselves. The network heals. One of those two carts quietly stops existing. Nothing in that story is a bug. It is a choice somebody configured. It is called the cap theorem, and almost everybody learns it wrong. I'm Nancy, and this is Trust Boundary. Every episode, we take one piece of your stack apart and find the line where trust changes hands, how it really works, what it looks like on the wire, and the one check almost everybody skips. By the end of this, you will read that trade-off straight off a config file. 1. What the three letters actually mean because two of them are not what you think. 2. Why you never pick two of three, that framing is simply wrong. 3. The line in your own database config that already made the choice for you. And the failure that happens when both halves of a break say yes. Start with the definitions because the definitions carry all the weight. 3 replicas of the same data, one client and one row. The replicas are the held side. You never see them directly. You see exactly one thing. The answer, the cluster hands back. Draw the line there. Trust changes hands at the acknowledgement. Everything left of it is what your application has already been told. Everything right of it is what the cluster can actually still prove. In a healthy cluster, those two agree and nobody thinks about the line. You send one write. The node you connected to fans it out to the replicas. Then it waits, not for all of them, for enough of them. Enough is a number you set, and it is called the write quorum. With 3 replicas, 2 is the usual choice for that number. 2 replicas confirm they hold it. That is a quorum. Only now does the acknowledgement cross the line. You get your 200 OK, and it means 2 replicas hold this value. Now the network breaks, 1 replica is on the far side of it. Nothing died. The two halves simply cannot hear each other anymore. This is a partition, and it is the P in cap. You do not get to opt out of it. Packets get lost. A system that spans a network cannot choose to never be split. So the real question is much narrower than picking 2 of 3. The question is what the cluster does in the seconds it is split. It has exactly 2 options, and every database picks one of them. Option 1, refuse. The side without a quorum stops answering. Your write fails. You get an error instead of a lie. That is consistency chosen over availability, and it is what etcd does. Option 2, answer anyway, with whatever replicas you can still reach. Your write succeeds on one side, the other side never hears about it. That is availability chosen over consistency, and the two sides now differ. Neither one is the safe option. They fail in completely different ways. And the choice was not made by your database. It was made by you. Here is the arithmetic, and it is the whole of the practical theory. N is how many replicas hold the row, say 3. W is how many must confirm a write before you are told yes. R is how many must answer a read before you are handed a value. Set W to 2 and R to 2 across 3 replicas. 2 plus 2 is 4, and 4 is greater than 3. So any read set and any write set share at least one replica. That shared replica is the one holding the last write you were told about. That overlap is what a strong read actually is. Arithmetic, not magic. Be careful here, overlap guarantees you see the last acknowledged write. It does not give you a single global order over every operation. Now the artifact? This is not theory, it is a line in your config. In MongoDB, it is the write concern, and majority is the word that matters. In Cassandra, it is a consistency level set per statement, not per cluster. In DynamoDB, a ret is eventually consistent unless you ask for the other kind. The same cluster can be strict for one query and loose for the next. Go back to the checkout service and turn availability all the way up. The break happens. 2 customers touch the same cart. One request lands left of the break, one lands right of it. Both sides have replicas. Both sides reach their own quorum of 1. Both sides acknowledge. Both customers see a success screen. 2 acknowledgements cross the line and they contradict each other. This is split brain, and nothing on either side detected it. 40 seconds later, the network heals and the replicas start talking again. Now there are 2 versions of one row and something has to pick. The most common rule is also the simplest, last write wins. The write with the later timestamp survives, the other one is discarded. Not merged, not flagged, discarded, and no error is ever raised. Cassandra documents this, including what clock skew does to it. If 2 nodes disagree about the time, the wrong write can win. That is the failure. Now notice where it actually happened. It happened at the acknowledgement, long before the data diverged. The cluster promised something it could not prove, and you built on it. The fix is never a smarter merge, it is a stricter promise. Require a majority, and the losing side cannot acknowledge anything at all. You trade a working checkout for a checkout that refuses. That is the deal. Every part of a distributed database has a real trust line except one. Replication is real, the quorum is real, the commit is real. All of it is arithmetic the cluster can actually check. And all of it stops the moment the acknowledgement leaves the cluster. After that, it is only a fact your application has decided to believe. So the question is never whether your database is consistent. It is what your database says while it cannot prove anything. There's a second half to this, and it has an ugly name, PACELC. Even with no partition at all, you are trading consistency against latency. Waiting for a second replica costs you time on every single write. Go and open your database config today. Find one line. Your write concern or your consistency level. Read what it says. If it does not say majority, you have already chosen to stay available. Every system has a line where trust changes hands. In a distributed database, it sits at the acknowledgement. That is one more boundary drawn. If this made something in your stack, click subscribe. There's a new one every day, and the next one is already in the queue. I'm Nancy. I will see you at the next boundary.